All right, so we gotta kind of set the stage for this a little bit. So this next topic, this is a very applied topic. This is something that we do a lot, like in engineering, for example. A lot of times when you're trying to just do a quick calculation, it's easier to use a linear approximation than it is to use an exact function if the function is real curvy and inconvenient, right? So what we're going to talk about is linearization. That's probably all we'll get to today, but that leads us into some other interesting topics. We can talk about differential forms of derivatives. So essentially, there's a new way that we could take all the derivatives that we already know and we could just tweak them very slightly, and essentially for free, we get new forms of those derivatives called differential forms, which have really interesting applications. We can make differential approximations that are really quick and easy to do, that oftentimes are very accurate. And we'll talk about when they're accurate and when they're not. And you'll have a good feel for that already. So first thing we run into, oh, what the heck happened here? Well, I guess that's right. Oh, darn it anyway. Here I had this great thing built. Oh, man. Let me see. Oh, okay, that's really a bummer. So this thing was supposed to be, oh well, anyway. Okay. Okay, so what do we know here? So if we're trying to make a linear approximation, all this is, this can be really a simple concept. All we're going to do is we're just going to use the equation of a convenient tangent line to approximate the curve. That's it, right? So to begin with, if we know we're at the point, we're just going to pick A is going to be some convenient value that's easy to plug in and evaluate our function at. Okay. If we know that that's a really convenient point on our function, well then we're going to go ahead and let that be the point of tangency, right? So if we want to come up with the equation of a tangent line, all we're doing is we're using point slope. Y minus a known y value, right? The y coordinate of a convenient point equals m times x minus the x coordinate of that convenient point, right? So really this is just like saying y1, and that's like saying x1, right? Okay? So then what's our slope? Well, our slope, that's calculus, right? Our slope is just going to be the value of the derivative of the function at the point of tangency. Isn't that just what a derivative means? It's the slope of a curve, which is the same thing as the slope of the tangent to the curve at whatever value I'm plugging in. For us, we're plugging in the convenient place, which is at x equals a, okay? So then if we plug that value in for m, look what we get. Y minus y1, which is f of a, equals m, which is f prime of a, times x minus x1, and x1 is a, right? And if we solve that for y, what do we get? Well, we get the equation of the line, right? Y equals m, I mean, this is really like saying it's just going to be some constant plus m times the quantity x minus a. That's just the equation of a line. If I wanted to put that into slope-intercept form, all I would have to do is distribute this number and add up the constants, and it would be in slope-intercept form. We don't have to do that, but we could, right? So we call that, instead of calling it y now, we're going to call it the linearization. That is the new function, the tangent to the curve that approximates the curve, as long as we don't go too far away. right? If I'm staying pretty close to the point of tangency, the tangent line is going to match the curve pretty well. If I go too far away, the tangent line is going to deviate from the curve, and this may not be a good approximation, okay? But if we just trade that y for L of x for linearization, then this is the formula we're always going to come up with. It's just f of a plus f prime of a times the quantity x minus a. Where again, what is a? A is just a convenient place that's close to some value of x that we want to explore. Okay? So let's try this. What if we want to take the function f of x equals 2 over x, and we want to approximate f of 2.1? Well, 2.1 is pretty close to what convenient value? What would be a convenient value of x that we could plug in and easily evaluate that's close to 2.1? 2, right? What's f of 2? 1. That's an easy one to do, isn't it? Right? So that's going to be the value that we would choose for a. The convenient value of x would be a equals 2, right? Oops. Okay? We picked 2 because it's a convenient value of x. Okay, so if that's our convenient value, then what is L of x? What's our linearization going to be? Right? It's going to be f of a, which is, what's a? 2. So f of 2 plus f prime of 2 times x minus 2. That's it. Whoops. Didn't want to do that. Okay? Well, what is f prime of x? If f of x is 2 over x, what's f prime of x? Would I use quotient rule? Yeah, use the power rule. Make that a 2x to the minus 1, right? And what do you get? Negative 2x to the negative 2, which is really just what? Negative 2 over x squared. Yeah. Right? Okay, so then now we can evaluate these. You guys already told me f of 2 is what? 1. And what would f prime of 2 be? Negative 1/2. Okay, good. Everybody see that? Okay. Okay, questions so far?
What do those dots mean?
The 3 dots mean therefore. Yeah. I mean, essentially, it's, yeah. Yeah. They mean, it's a Latin expression, but it means therefore. Yeah. So then we can be more specific then. What is our linearization if we actually plug in values? Well, f of 2 is 1, we said, right? F prime of 2 was negative 1/2 times x minus 2. So don't we just get that? Yeah. Everybody agree? Okay, so that's our line. That's the line that approximates our function for values close to 2. So then we could estimate what f of 2.1 is by just calculating L of 2.1. Okay, what's that going to give us? Well, L of 2.1 is going to be what then? There's L of x. 1 minus 1 minus 2.1 minus 2 over 2, right? Which is just 1 minus 0.1 over 2, which is what? 1.95, right? Okay? I mean, that's just a number we're going to get, okay? Make sense? Okay. How can you get what is 0.1 over 2? That's the same as 1 over what? 0.1 over 2 is the same as 1 over 20. Okay, well, what's 1 over 20? If 1 over 10 is 0.1, what's 1 over 20? 0.05, 0.05. So 1 minus 0.05 is, oh, that should be, that's wrong, isn't it? That should be,
Oh, it should be just point.
yeah, it should be 0.95, right? 0.95. Make sense? So we got a pretty good estimate of what f of 2.1 is. F of 2.1, it's not going to be exact, but it's going to be pretty close. Okay? Okay, so when are we out of here? 6 minutes. Okay, so then we'll just talk about this page and call her good. So a similar approach is to use differentials, right? So this is just going to be a parallel way of looking at this. So differentials, they estimate the change in a function's output for small changes in the input value. That's what a differential does. So they provide a means of easily estimating a function's response to a small input change. This is frequently something we want to do like in engineering. Like if we were to change, let's say you're building, you're manufacturing ball bearings. If the tolerance for the radius in a ball bearing is, let's say you can get the radius to within, I don't know, 0.003 of an inch or something. But there's a really tight tolerance on the mass, therefore the volume of the ball bearing. You need to know like how much is a small change in radius going to impact the volume, right? That's going to create some propagated change in the volume also, right? So whatever your manufacturing error is in radius is going to create a propagated mass error in the ball bearing, right? And you got to know if that's going to meet your tolerances for those ball bearings you're manufacturing. And so differential is a quick way to get a pretty good estimate of if that's going to work or not, okay? So what is a differential? It's so simple. All a differential is literally what you get if you take a normal derivative, like we're used to, dy dx is f prime of x, right? Those are just two different names for a derivative. Dy dx equals f prime of x, and we're just going to multiply each side by dx. What's that give us? Dy equals f prime of x dx. Okay, that one little change completely changed the meaning of the derivative. Instead of being a slope of a tangent line now, what this is telling us is this is saying a small tweak in the input variable x creates this tweak in the output variable y. Okay? So, whoops. So let's find some differentials here. It's super easy to do. So if y equals tangent x, what's dy? Well, what's the derivative of tangent x? So it's secant squared x times dx, done. That's it. It's whatever the derivative of that function is times dx. Okay, how about this one? Oh man, this got all messed up. Shoot. I don't know how this got so messed up. Is that it right? I don't know how that got so messed up. Huh. Okay, so what about this one? What if we've got f of x equals sine squared? This is a really complicated, it's a bunch of different functions of functions, many layers to this, right? Well, if that's f of x, what's dy going to be, the differential? It's just going to be the derivative of that whole thing times dx. Well, let's get a little practice here. What is the outside layer of this function? Okay, but what's the outside? You told me 2. I want to know what's the outside layer. It's a squared, isn't it? Right? Because sine squared means the quantity sine squared. Agreed? Okay, so the outside layer would be this. The outside layer is that 2. So if I'm going to differentiate, the first layer is going to be 2 times sine of all that stuff, right, to the first power. Okay, Okay, what's the next layer? Inside the squared would be what? Okay, so then what's the derivative of sine of hand? Okay, so then we're going to get a cosine of x cubed plus 1 times, what's the final layer? X cubed plus 1. The derivative of x cubed plus 1 is 3x squared. Okay. Oops. Times dx at the end, because this whole thing right here, if we call this f of x, what is this whole part right there? If that's f of x, what's that? F prime of x. And the differential form of the derivative is just f prime of x times dx. Now, if I just combine stuff, 3x squared times 2 is 6x squared. There's my sine, there's my cosine, there's my dx, right? So we just calculated a big differential. Okay?
It's a cliff.
Okay. We'll pick up tomorrow with some stuff.